So we saw Thursday that when you solve a system of equations, you're looking for the point of intersection between the two lines. A linear system of equations is where you have two or more equations that are together in a group. And so on Thursday, we looked at systems of equations where you had two different linear equations. We learned that the solution is the point of intersection between the two lines. We saw that that can be done graphically. If you're really careful and you draw nice accurate graphs, then you can do them on your paper. We also saw that you can use your graphing calculator to check. Here's your package. Go get it really fast. Okay, so the solution is the point of intersection between the two lines. And so because of that, every point that's on a line is a point that satisfies the equation of that line. So if you have one point that is the solution where the two lines intersect, that one point will satisfy both equations. And so we would use that for example 2. Some guy named Guy solved the linear system and found the solution to be 2, -5. Verify whether Guy's solution is correct. So there's two ways you could do this. You could actually solve the system of equations. You could put both equations in y equals mx plus b form. You could graph them on a paper or on your calculator and find the point of intersection. But the other way, without actually solving, is to verify that that point 2, -5 does satisfy both equations, meaning that the equation should be true. Left side and right side should be equal. If you let x equal 2 and y equal -5 in the equation. So that's what I'm doing here. I'm letting x equal 2 and y equal -5. So -2 times -5 is +10, and 2 plus 10 equals 12, which is what the number on the right side is. So that shows that that point works for the first equation. It works for the first equation. But we need to make sure that it works for the second equation as well. All we've really shown right now is that the point 2, -5 is on that first equation. We need to make sure that it works for the second equation as well, and if it does, if it satisfies both equations, then that confirms that it is the point of intersection. It is the solution. So we'll let x equal 2 and y equal -5 in both equations, and you're going to have 6. 3 times 2 is 6, and -2 times -5 is +10, and this gives us 16, not 4. So it doesn't equal. Therefore, it is not the solution. And that's all it asks us to do. Determine whether or not Guy's solution is correct. So obviously he made a mistake somewhere when he solved that system of equations. Because a point 2, -5 does not satisfy that second equation. Natty has saved $16 and her sister Lucia has saved $34. They've just started part-time jobs. Each day that they work, Nadia adds $5 to her savings. Lucia adds $2. The girls want to know if they will ever have the same amount of money, and if so, what will that amount be on and on what day? So if x is the number of days and y is the amount of money saved, then we have two equations. Here's Nadia's equation, 5x plus 16, because she started with $16 saved, and she adds $5 a day onto it. So the 5x will represent how much she saves each day, plus the 16 that she started with. Lucia's equation is 2x plus 34. She started with $34, and she adds $2 every day. So that's what the 2x represents. X is the number of days. So we asked to solve this system graphically, and what does this solution mean? As we saw last week, if you have a graphing calculator, you can do this on the graphing calculator. You can put both equations in. The first one for Natty is 5x plus 16. The second one for Lucia is 2x plus 34. I'm going to set my windows to their standard setting by going zoom 6, and we want to see the point of intersection. Now, when I did that, I only see one of the lines. I don't see the point of intersection because I don't see the second line. And what that means is we need to change our windows. All right? One option we have on these calculators is choose what's known as zoom fit. So when I hit zoom, and I have to scroll down, but fit is this number 0 in this list. And when you choose that, the calculator picks the windows that should show the graphs. So I'm going to choose that. And there we go. We can see both lines now, and we can see the point of intersection. After doing this, if we still don't see the point of intersection, we have to change our windows ourselves. But in this case, we don't need to do that. We can find our point of intersection by going second function trace, number 5 for intersect, enter, enter, enter. And the intersection is at 6, 46. Our solution, our intersection is at 6, 46. Now remember, x is the number of days, and x is the first number in your ordered pair. Y represents the amount of money saved. So this tells us that after 6 days, the two girls will have the same amount of money earned or saved. They'll both have $46. After 6 days, both girls will have saved $46. I think you can see that it will be advantageous if you have a graphing calculator for this unit especially. Not only will it help you find some answers, but it'll also help you check the answers you do find. When we go into chapter 9, we're going to learn how to solve these systems algebraically without drawing a graph. But you can still use the graphing calculator to check to make sure the answer that you got is the correct answer. Right, so if you can get a graphing calculator, that would be helpful. The library usually has some that can be signed out every semester, so you might want to check at the library as well. But if you get your own and take care of it and learn how to use it, you will use it for sure next year and in grade 12. If you take math all 3 years, you'll use that graphing calculator. Okay. Without it, you'd have to draw the graph and do that manually. Right? You'd have to draw a graph and do it carefully, because otherwise, if you don't do it carefully, you probably won't get the right answer. Example 4, people can rent ski and snowboard equipment from 2 places at Winterland Resort. Option A charges a one-time fee of $30 plus $8 an hour. Option B is just straight $14 an hour. If C represents the cost in dollars and T represents the length of time and hours of the rental, in this case, we need to create our system of equations. We need to write the equations for each of these scenarios. C is the cost in dollars. And for option A, they have a one-time fee of $30, no matter what you must pay that, plus $8 per hour. And we're told that T represents the length of time in hours. So that would be an equation for option A. For option B, our equation is just C equals 14T. There is no initial fee. It's just straight $14 an hour. So there's the two equations. So this is one of the skills that you're going to have to learn, is to write the equations from the information you're given. And we want to solve this system graphically, so we will use our graphing calculator for this. Go to y equals, clear that first equation, and replace it with 30 plus 8. Now there is no other variable in our calculator except x. So even though we have 8t written down, the only variable we have to use in our calculator is the variable x. So there's that first equation. The second equation is just 14x. And I'm going to go zoom fit, zoom 0, so the calculator chooses the windows for us. We need to see both lines, but more importantly, we need to see that point of intersection, which we do. Second function trace, number 5 for intersect, enter, enter, enter. There's our solution, the 0.5 comma 70. You don't have your booklet? We'll run and get it really fast. So, this is not in terms of x and y. Our equations are not in terms of x and y. But remember, the first number in the table, first number in the ordered pair, is your independent value. Normally that's x, but it is the independent value. It is the variable that's in the equation. In this case, that represents t, the time in hours. The second number is your dependent variable. It's the one that is isolated by itself, which is c. The total cost that you have to pay will depend on how many hours you rent the equipment. Cost depends on the time that you rent the equipment. So time is independent. That always comes first in a table of values. It always comes first in a set of ordered pair. Cost is the dependent variable. It always comes second. All right, so what does this solution represent? Well, it represents that after 5 hours, each plan will cost $70. Now, to verify the solution, we'll look back up at the scenarios. Plan A is a flat rate of $30 plus $8 per hour. And in this case here, we're saying that the number of hours is 5. So that'll give us 30 plus 8 times 5 is 40, which gives us our answer of $70. Plan B is straight $14 an hour. And if you go 14 times 5, that also gives you the $70. So there we checked it. We didn't really use the equations we wrote. What we did is looked up above and matched it to the scenario. Plan A started with the $30 fee and then $8 per hour. Now that is what the equation tells us, but if you made a mistake writing your equation, the answer you found on your calculator will be correct for the equations you wrote, but it might not match the scenario if you made a mistake writing the equation from the scenario. So always go back to the scenarios to make sure that your answer works for the scenarios. Okay, so there's that one done. And again, having the graphing calculator is quite advantageous. So again, relations can be represented numerically using a table of values. They can be represented graphically and verified algebraically. A system of linear equations is often referred to as a linear system. It's where you have 2 or more linear equations involving common variables. In this course, we'll only be using 2 equations. If you go into 20-1, you'll actually look at examples where you have more than 2 equations, or you might have a linear equation and a nonlinear, a curve, that you need to find the point of intersection of. And you can do those graphically using the graphing calculator. And then we're also going to learn in the next chapter how to do them algebraically. Where you're not actually graphing, you're doing it algebraically. Again, a solution to a system of equations is the point of intersection of the lines on a graph. It's an ordered pair that satisfies both equations. It's a pair of values occurring in the tables of values of both equations. Okay, so you can check them graphically, and then as we have been doing, you can verify them algebraically, making sure that that point satisfies all of the equations. So if we go on to this next example, David D earns $40 plus $10 per hour. Carmen just earns, $50 plus $8 per hour. We want to represent the linear system numerically and graphically, and then identify the solution and what does it represent. So we have to start by writing our equations, and in this case, we need to start that process by choosing our variables. So we might let A, and it can be any variable you want, but I'm going to let A equal the amount earned. So this will be for each person. And maybe we'll let N equal the number of hours worked. On the last example, the variables were designated for us. In this case, they're not. So that's where we need to start. Our next step then is to write our equation. So for David E, the amount for David E starts with $40 plus, then it's $10 for every hour, and N is the number of hours. For Carmen, Carmen's amount starts with 50 and gets $8 per hour, where again N is the number of hours. So there's our two equations. So these two steps are all part of part A, representing the linear systems, relating the earnings numerically, and we've written the equations, so that's our numerical part, and then we can use them to do the graphical part to find the solution, and then also explain what it represents. So we put these equations in the calculator. The first one is 40 plus 10x. The second one is 50 plus 8x. We need to find the point of intersection. Again, I'm going to go zoom 0, which will select the windows for us. We need to see that point of intersection, and we do. So now we can find it by going second function trace, number 5 for intersect, enter, enter, enter. And there's our point of intersection, the 0.5, 90. So part B, the point of intersection is the 0.5, 90. Now, when I wrote the equation, remember the independent variable is the variable that's in the equation. That's always the first number in the ordered pair, which is N. N, the number of hours worked, is independent. A, the amount, is the variable outside the equation. It is the dependent variable. The amount that a person earns depends on how many hours they work. So A is dependent on N. N is independent, A is dependent, which means that after 5 hours, they will have both earned $90. And if we check that, what we're told up above, so for David D, if David D works for 5 hours, it's $40 plus $10 per hour. And they're going to work 5 hours. So 5 times 10 is 50. 40 plus 50 does equal 90. So it works for David E. After 5 hours, David E. earns $90. So now we'll also check for Carmen. So for Carmen, starts with $50 and then earns $8 per hour. And again, we're saying that they're working for 5 hours. 8 times 5 is 40. 50 plus 40 is 90. So it works for both. In each case, when n is 5, A is 90. So again, we check it going back using the scenarios, not the equations. If you made a mistake with your equations and then you checked using those equations, well, they'd work for the equations if you did everything right. But if your equation doesn't match the scenarios, then it means that none of it's right. Okay? So again, as a review, to solve systems by graphing, if you're going to graph them, you want them in slope-intercept form, which this first one is, and the second one. They're both in slope-intercept form. Y equals mx plus b, where m, the slope, is a number in front of x, which in this case is 1. But remember, we've always said slope is rise over run, so you need to write it as a fraction by putting it over 1. 1 over 1, and b, our y-intercept, is at 2. Now remember, this is where the graph crosses the y-axis. You don't go left or right to get to a place on the y-axis, which means x is 0. So the point 0, 2 is where we start, always. Start with our y-intercept, and then we apply our slope multiple times, which is rise 1, run 1. Rise 1, run 1. You could also rise -1 and run -1. Rise -1 and run -1. Goes through all those points. Our slope is +1, which means as you go left to right, it must rise, which this line does. Right? So there's that line with arrows on the end. And the second line, y equals -2x plus 5. So that's m, our slope of -2 over 1. And our y-intercept. Again, that's where the graph crosses the y-axis. The x value is always 0. We start at the point 0, 5. And then we rise -2 and run +1. Rise -2 and run +1. We could also rise +2 and run -1. Rise +2 and run -1. And there's that line. And remember, whenever you draw your lines, you need to have arrows on both ends. A line is a relation that continues at a constant rate of change. That rate of change is a slope, and it goes forever in both directions. We can see that the point of intersection appears to be the point 1, 3, and we can check it. We can check it algebraically if we want. If you don't have a graphing calculator, this is how you would check it algebraically. Make sure that that point satisfies both equations. When x is 1, y should equal 3. And it works for the first equation. When you let x equal 1 and y equal 3, you get the same number on both sides. Left side equals the right side, which means it is correct. It is a correct point for that equation. That point lies on that first equation. But we need to make sure it works for the second equation as well. Again, we'll let x equal 1 and y equal 3 and work it out. So on the right side, -2 times 1 is -2, plus 5 does equal +3. You get the same thing on both sides. So we've just checked it. We've shown that this point is the correct point of intersection. It satisfies both equations, so it is the point of intersection. Okay, and so there is also a solution doing what we just did. We checked it using the two equations. So try this one on your own. The grid is there for you, so you can do it. If you have a graphing calculator, once you find your answer, use your graphing calculator to check. Have a good day. Make sure you check Google Classroom to see what the assignment is. So for the first line, because these are both in slope-intercept form, m the slope is the number in front of x, and our y-intercept is the constant. Remember, it's always where x is 0. It's where the graph crosses the y-axis. You don't go left or right to get there. That's the reason that x is 0. So we start at the y-intercept of -3. Our slope is always written as a fraction because it's rise over run. So 2 is written as 2 over 1. So you'll rise 2 and run 1. Rise 2 and run 1. You could also rise -2 and run -1. Rise -2 and run -1. So there's that line. Again, the second line is in slope-intercept form, and the slope is a number in front of x, which is 1. Even though there's no 1 there, we know x means 1x. There is 1x there. And we always write it as a fraction, so it's rise over run. Our y-intercept is the constant, which is where x is 0. It's 0, -1. And then we'll rise 1 and run 1. Rise 1 and run 1. You can also rise -1 and run -1. Rise -1 and run -1. Both of these slopes have a positive slope, so they both rise as you go left to right, which they do. And so it looks like our point of intersection is the point 2, 1. And we can check that using the original equations. Y is 1, x is 2. So on the right side, 2 times 2 is 4, and 4 take away 3 is 1. So it works for the first equation. Checking the second equation. Y is 1, x is 2, and 2 minus 1 does equal 1. So it works. We get the same number on both sides. Proves that that point is on both lines. So therefore it is the solution to the system of equations. It's the point that satisfies both lines. Right, so the solution as well as the check is on the next page. This next one, you want to solve the system of equations, identify the point of intersections, and then verify. So these ones are not in slope-intercept form, so that's where we need to start. Now you could, if you wanted to, we learned in chapter 6, you can find the intercepts, the x and y intercepts. That's another thing that you can do to graph it. But I'm going to put them in slope-intercept form. So that means getting positive y by itself. So for this first equation, you need to subtract the 2x from both sides. And so you'll get negative 2x plus 2. The second equation, x minus y equals 7. If you subtract the x from both sides, it's still a negative y on the left. That'll be negative x plus 7. And now you have to divide both sides for everything by negative 1. And y will equal x minus 7 when you do that. So the first line, m the slope is negative 2 over 1. Our y-intercept is the point 0, 2. Our second line, m the slope is 1 over 1. Our y-intercept is 0, negative 7. So if I graph that second line first, 1, 2, 3, 4, 5, 6, negative 7 is there. And then we rise 1 and run 1. Rise 1 and run 1. We can also rise negative 1 and run negative 1. That works as well. So here's our line. Looking something like that. And again, we put arrows on the ends. Our second line has a y-intercept of 0, positive 2, and a slope of negative 2 over 1. So you're going to rise negative 2 and run 1. Rise negative 2 and run 1. You could also rise positive 2 and run negative 1 if you wanted to. Rise positive 2 and run negative 1. But what you need is the point of intersection, which we can see where that is, even without drawing the line, because when we rose negative 2 and ran 1, we actually ended up on the other line on one of those points. So that's that point right there, which is the point 1, 2, 3, negative 4. And when you're checking, you want to use the original equations. If you made a mistake when you converted to slope-intercept form, the answer you got should match that equation that you wrote by getting y by itself for both equations. But if you made a mistake getting y by itself, it's not going to show up. So you always start with the original equations. And our point was 3, negative 4. Two times 3 is 6, and 6 minus 4 is 2. So it works for that one. The second equation, x minus y equals 7. Again, checking the point 3, negative 4. 3 minus negative 4 becomes 3 plus 4, which is 7. So it checks. When you check the original equations, they both work. They both make the equations true. So we just confirmed that that is the solution to the system of equations. This one says verify by graphing and one other way that 3, negative 2 is a solution to the system. So that other way will be the manual check that we do. In this case, they're giving us a solution. We're going to verify it by graphing first. Remember, one option to graphing is by finding the intercepts. We can find our x-intercept. Remember, that's always where y equals 0. If you let y equal 0, the y term will disappear. 3 times 0 is 0, and x minus 0 is just x. You'll get x equals 9. And that was where y was 0. So in this case here, we're going to kind of have to guesstimate where that is because our graph grid ends at 8. So we're kind of guessing where it is. Our second step is to find the y-intercept by letting x equal 0. So 0 take away 3y equals 9. So again, the x term essentially disappears. You're just left with negative 3y equals 9. And we divide both sides by negative 3. Y equals negative 3. That's where x was 0. That's the point 0, negative 3. That's right there. So this gives us 2 points to graph our line. So the line looks something like that. Now our second line, 2x plus y equals 4. Again, our x-intercept is where y equals 0. That y term just disappears, so you'll have 2x equals 4, and dividing by 2 means that x equals 2. So that is the point 2, comma 0. That's that point. Our y-intercept is where x equals 0. So that x term disappears. You're just going to have 0 plus y, or y equaling 4. So that is the point 0, comma 4. That's up here. So now we'll draw our line through those 2 points. And we're going to assume that our point of intersection is a point where the x and y are integers. 1, 2, 3, comma negative 2. Which matches the solution. So we just verified it graphically. I think this also shows you that slope-intercept form is a quicker way to graph a line too. It would have been much quicker to use y equals mx plus b to graph these lines. So that's one way. The other way is part of our check. What bet? No. No. One bet only. Can't afford it if I lose. Can't afford it. So x minus 3y equals 9. So when I let x equal 3 and y equal negative 2, negative 3 times negative 2 is plus 6, and 3 plus 6 does equal 9. So it checks for the first equation. Now here's our second check. Two times 3 is 6, and 6 minus 2 does equal 4. So it checks for that as well. So there's our 2 ways. We checked it by actually graphing it, and then we checked it by verifying that that point does satisfy both equations. And so then that's what you do for these ones. To verify whether the given point is a solution, it has to be the point that satisfies both equations. And so when you check that first equation, 3 times x, which is 2, minus y, which is 5, gives us 6 minus 5, which is 1. That does not equal 2. That does not equal 2. So you don't even have to check the second equation. This is not the solution. Two comma 5 is not the solution because it doesn't even work for the first equation. And it actually doesn't work for the second equation either. When you let x equal 2 and y equal 5, you're going to get 2 plus 20, which is 22, not 32. But the fact that it doesn't work for the first equation is all you really need to show. It's not the solution. So now let's check for question B. See if negative 3, negative 2 is the solution to that system. So letting x equal negative 3 and y equal negative 2 in the first equation gives us negative 6 plus negative 6, which does equal negative 12. So that shows that that point does lie on the first line. But we also have to see that it is on the second line as well. Four times 3 is negative 3, is negative 12. Negative 3 times negative 2 is positive 6, and negative 12 plus 6 is negative 6. You get the same thing on both sides. So negative 3 comma 2 is the solution. So explain what the results would show on the graph. That means that negative 3 comma 2 is the point of intersection. And in the first case, we've established that 2 comma 5 is not on either graph. So that means that 2 comma 5, again, is not a point on either line. So it can't be the point of intersection because it's not on either of those two lines. Okay? So we're going to stop there for today. Your homework is on page 428 to 430, 10, 11, 17, 18. And you're going to hand this one in for marks. Okay? There is graph paper up here, and I will get some more out for you if you need more. Because you have to graph all of these systems and get the point of intersection. And that's only going to work if you do it very carefully. Right? If you have a graphing calculator, you can use that to check your answers. But you have to show the graphs for this assignment that's due for marks. So there's graph paper up here if you need it.